Hello everybody, my name is Axel Feldman.
And my name is Nikola Samardzic. It is our great pleasure to be here and to introduce F1, an accelerator for computation on encrypted data. This is a joint work with Alexander Kristev and Professors Srini Devadas, Ron Dreslinsky, Chris Pikert, and Daniel Sanchez. Let's start with talking about what fully homomorphic encryption is. Many institutions today have sensitive or private data. Often, extracting valuable information from this data requires substantial compute resources. This forces institutions to share their sensitive data with cloud providers. Unfortunately, the sensitive data is now vulnerable to breaches of the cloud provider's infrastructure. Fully homomorphic encryption, or FHE, is a cryptographic system that enables computation on encrypted data. This technology allows us to encrypt our sensitive data before sending it to the cloud. Using FHE algorithms, the cloud provider then performs computation on encrypted data and returns the encrypted result. As the data is encrypted throughout the computation, breaches of the cloud do not expose our data. The cloud then returns the encrypted result, and we are able to decrypt it with our cryptographic key. So as mentioned, FHE is a cryptographic system that enables computation on encrypted data. Specifically, FHE allows us to perform arithmetic operations on encrypted vectors. Although FHE isn't Turing complete, it is expressive enough to be used for neural networks, logistic regression, database lookup, and many other tasks. The key downside that prohibits wide adoption of FHE is that it is about 10,000 times slower in software than doing the same work on unencrypted data. We address this problem by proposing F1, an accelerator for FHE that bridges the performance gap between encrypted and unencrypted computation. An example use case for FHE is running a DNN inference where the computation is too expensive for the client, but the data on the client must also remain private. The illustration shows how a DNN inference that recognizes faces can be safely offloaded to a remote server via FHE. Current state-of-the-art approaches need 20 minutes to perform a single DNN inference using FHE. Our accelerator pushes this down to 250 milliseconds, a speedup of over 5,000x. This means F1 is the first to enable real-time private deep learning in the cloud using FHE. I'll hand the presentation over to Axel now.
Thanks, Nikola. Here's the agenda for the rest of this talk. We'll give a quick overview of FHE computations, present some architectural insights on accelerating FHE, discuss the design of our accelerator, F1, then wrap up with our results. During this part of the presentation, we'd like to give you a flavor of what FHE computations look like. We'll start with the data types. We take a message M, which is composed of some relatively small plaintext values. We add some noise for security, and then encrypt it using a secret key to generate a pair of polynomials. We'll not cover encryption in more detail because it happens on the client, not the server. These polynomials represent an encryption of your message, which can now be used in homomorphic computations. Once we have our ciphertext, we can now start to do computations on the encrypted data. By computing on these polynomials, we can add, multiply, and rotate the encrypted plaintext values. That isn't to say that simply multiplying two ciphertext polynomials will multiply the underlying elements. The operations we apply to ciphertexts are often much more complex than the effect they have on the underlying elements. For example, to multiply two ciphertexts x and y, we need to go through this complex algorithm. We need to perform a set of polynomial multiplications and additions, in addition to an extremely expensive key-switching algorithm. This key-switching algorithm can take tens of polynomial operations and is by far the costliest part of all FHE computations. It also requires many megabytes of auxiliary data in the form of key-switch hints. One important thing to note is that the multiplications in this figure are actually expensive polynomial multiplications, not straightforward scalar multiplies. Let's now dive a bit deeper into that part. If we want to multiply two polynomials, we need to convolve their coefficients. Naively, this involves multiplying each coefficient of one polynomial with each coefficient of the other. This takes n-squared multiplies. However, we can use an efficient convolution called a number-theoretic transform, which is very similar to an FFT, except with modular arithmetic, to reduce our number of multiplies to n log n. This is absolutely critical, as our polynomials often have over 16,000 coefficients. To efficiently run FHE computations, F1 must accelerate NTTs. Let's zoom out a bit and talk about the broad structure of an FHE program. Thinking back a few slides, when we encrypt a ciphertext, we add in a bit of noise. The bit width of our coefficients represents our noise budget. As we compute deeper and deeper on ciphertext, we use up our noise budget and shrink the bit width of our coefficients through modding down. The problem really comes in when we run out of noise. When we no longer have any noise budget to proceed, we're stuck. We can't perform any more computation without making our values undecryptable. Fortunately, FHE has a trick up its sleeve. We can apply an expensive procedure called bootstrapping, which allows us to refresh our ciphertext noise budgets. An important corollary of all this is that it emphasizes the ability to be able to compute on polynomials at multiple coefficient bit widths. This underlines a key challenge. We start off with very wide coefficients, sometimes around 1,000 bits. Multipliers scale poorly in bit width, so having 1,000 bit multipliers would take up a ton of area on chip. Over the course of running a program, we'll end up computing on much narrower coefficients, so the flexibility is also important. We use a classic cryptography trick called the residue number system, RNS, where instead of representing each coefficient as a 1,000-bit number, we represent it as many coefficients, each modulo a smaller prime. To apply operations to the wide polynomial, we can simply apply those same operations independently to the corresponding pairs of residue polynomials. Using RNS allows us to perform wide polynomial arithmetic using 32-bit data paths. Furthermore, it allows us to efficiently perform computations at different bit widths. We don't have some fixed 1,000-bit multiplier. If we want to compute on something narrower, we simply have fewer residue polynomials to compute on. We will now analyze some of the architectural characteristics of FHE. Now that we've gotten a bit of a taste for FHE computations, let's talk about what we need to do to design an effective FHE accelerator. First, FHE isn't a single application. We're not accelerating encryption or decryption. We're accelerating the computations on encrypted data. These computations are general purpose, and we want to accelerate all of them. While these computations are quite diverse, they all rely on big polynomial arithmetic. It is important to accelerate the primitive operations in a composable way. Third, our operands are very large. Ciphertext can take up to several megabytes, and key switch hints, which we briefly saw earlier, can take tens of megabytes. Data movement is absolutely key. Finally, our data flow is completely static. Data-dependent branches are not possible in FHE, allowing us to know all control flow ahead of time. We'll cover all of these points in a bit more detail. FHE isn't a single algorithm. It's a style of computation on encrypted data. People have already implemented neural networks, linear algebra, logistic regression, and much more. Not only that, but FHE is also a fast-moving field. These algorithms are constantly evolving. As a result, we design our accelerator to be fully programmable. It doesn't just support a single application or a single set of encryption parameters. We design F1 such that, like a general-purpose CPU, new applications can be easily and efficiently executed on it. This is in contrast to prior work, which focuses on accelerating single FHE operations, while pushing remaining ones to the host CPU. We take this theme of programmability a step further. F1 accelerates primitives such as NTTs, modular multiplication, and modular addition. By accelerating primitives instead of larger functions, we admit a lot of algorithmic diversity. F1 supports multiple FHE schemes, and even within a single scheme, we allow for a lot of algorithmic choices. For instance, there are multiple ways to perform the key switching step of homomorphic multiplication, and all of them can be written composing the primitives F1 accelerates. Our design allows us to apply interesting algorithmic trade-offs to boost performance and also keep current with the latest methods in the FHE literature. Instead, prior work builds over-specialized pipelines to accelerate larger kernels, such as key switching. As mentioned earlier, our ciphertext and auxiliary data are huge. Minimizing off-chip data movement is therefore essential. To address this, we have a 64 megabyte scratch pad, and we decouple loads by explicitly fetching data ahead of time, all to avoid stalling on data movement. An important problem here is that the size of our operands limits our parallelism. Even with our large scratch pad, we can only fit a couple ciphertexts and hints on chip. This means that we can't just focus on functional unit throughput, but also functional unit latency. We address this through deeply specialized functional units designed to process operands extremely quickly. Prior work avoids these design challenges by targeting FPGAs, whose limited compute capabilities bypass the data movement challenges inherent in ASIC design. FHE computations are all completely static. There are no data-dependent branches because they are mathematically impossible. Intuitively, how can you branch on a value that you cannot even decrypt? This allows us to do all scheduling in software at compile time and avoid having expensive scheduling hardware on chip. It also allows us to decouple loads and mitigate the huge data movement penalties. To summarize, here are some of the principal differences between F1 and prior work on FHE accelerators. We target ASICs instead of FPGAs, forcing us to reckon with larger data movement problems. We accelerate entire FHE programs instead of only specific kernels. Finally, we accelerate primitive operations instead of building over-specialized pipelines. Let's move on to our accelerator's design. After considering all of these ideas, here's the architecture we settled on. We have a large, highly banked scratch pad connected to 16 compute clusters. Each cluster has a register file and 6 wide vector functional units, deeply specialized for FHE primitives. To help handle our off-chip data movement, we have 1 terabyte per second of main memory bandwidth. Each cluster has its own independent, statically scheduled instruction stream, avoiding the overheads of centralized VLIW-style control. We'll now start to discuss some of the interesting features of F1's design. We designed and implemented a complete software stack that compiles FHE programs expressed in a simple domain-specific language to scheduled F1 instructions. An FHE program written in our DSL precisely describes a data flow graph. Using the fact that we know all data dependencies ahead of time, we can schedule each instruction at a precise cycle. We can also manage our memory hierarchy statically, making sure that data is efficiently fetched ahead of time and replaced using a close approximation of the optimal Belides min algorithm. Our scheduling problem isn't entirely dissimilar from VLIW scheduling problems that have already been studied. However, our problem is much larger. Our programs have up to millions of instructions, and instead of a handful of registers, we have a scratchpad that stores thousands of individual residue polynomials. Existing VLIW algorithms we tried do not scale to our problem size, so we had to design our own. Our algorithm is designed to minimize off-chip data movement. We achieve this goal primarily by making sure that our large key switch hints are reused as much as possible between operations. By clustering operations around usage of the same key switch hint, we're able to utilize our main memory bandwidth effectively. I'm now going to hand the presentation back over to Nicola.
Thanks, Axel. So, F1 is built out of 4 basic functional units that accelerate primitive polynomial operations. These are the vector add and multiply units, as well as entity and automorphism units. An automorphism is a special permutation that is used to implement rotations on encrypted vectors. The key contributions are the novel fully pipelined automorphism unit and an entity unit with much higher throughput than prior accelerators. We now explore the design of the automorphism unit in more detail. To understand the challenges in implementing the automorphism unit, we first must understand how polynomials are stored and processed in F1. A residue polynomial is stored as a vector of up to 16,000 32-bit coefficients. The slide illustrates a toy 16-coefficient polynomial. Building a 16,000-lane vector data path is not practical and would be wasteful when shorter polynomials are used. Therefore, F1 divides the coefficients into chunks, each 128 coefficients wide. This means that the data path and memory system are made to process chunks instead of individual coefficients or entire polynomials. The slide illustrates dividing the 16-coefficient polynomial into 4 chunks, each holding 4 elements. The vector add and multiply units are easy to implement with this data path because they operate coefficient-wise on the residue polynomials. This means we can process data independently, chunk by chunk. In contrast, implementing the entity and automorphism units is hard. Each coefficient of the output may depend on any of the input coefficients. As coefficients of the input polynomial may be distributed across over 100 chunks, creating a pipeline data path that produces these outputs is non-trivial. This is a crucial reason why pure SIMD or GPU architectures do not work well for FHE. Here's an example automorphism applied to a 16-coefficient polynomial. Different colors represent different chunks of the input polynomial. This example demonstrates that automorphisms compute coefficients across chunks, making them hard to pipeline. We are the first to notice that an automorphism can be decomposed into a fully pipelined functional unit. The unit divides the automorphism into a pipeline of fixed permutations that operate only within chunks and not across chunks. To accomplish this, we first apply a set of permutations to each chunk, then transpose, then apply a different set of permutations, and finally transpose back. Again, this decomposition allows us to completely avoid permutations across chunks. Since all permutations are applied locally within chunks, they're cheap to implement and pipeline. At the core of a pipeline is a novel SRAM-based, fully pipelined matrix transpose subunit. This unit is also critical in the design of the NTT unit. Now let's explore our results. Here is the area and thermal design power, or TDP breakdown for F1. The chip has an area of 151 millimeters squared and consumes a maximum of 180 watts of power. We measure F1's performance on a diverse set of benchmarks, including neural network inference, logistic regression training, database lookup, and bootstrapping. Here's the speedup versus state-of-the-art on the LOLA neural networks, logistic regression, database lookup, and bootstrapping. This means F1 boasts a G-mean speedup of 5400x over state-of-the-art. Crucially, F1 speedups broaden the set of applications where FHE is practical. For example, F1 enables private, real-time DNN inference in the cloud using FHE. Now, all of F1's contributions are important. Here we show F1 speedups compared to if it used prior work's WIMP NTT design and the naive automorphism unit design. For the WIMP NTT and naive automorphism units, we use as many of them as is necessary to get the throughput to match that of F1's NTT and automorphism units respectively. Therefore, these results justify a conclusion that a small number of high-performance units works better than a large number of simpler ones. Again, this is because parallelism is severely limited by the low number of operands that can be stored on chip. Finally, we compare F1 scheduler performance to Goodman's very long instruction word, or VLIW scheduler. This demonstrates that standard VLIW scheduling techniques, like Goodman's scheduler, are not adequate for F1. In fact, for two of our benchmarks, Goodman's scheduler cannot even produce a valid schedule due to the large program size. This figure shows the breakdown of memory accesses between key switch hints, inputs, and intermediates. The figure also distinguishes between compulsory and non-compulsory loads. First, notice the large memory footprint of FHE programs, and recall that most programs here execute in about a millisecond. Second, notice the especially large footprint of compulsory key switch hint loads, shown in orange. This validates our choice of having the scheduler prioritize key switch hint reuse. To conclude, FHE has the potential to enable computational offloading with guaranteed security. But FHE's high computation overheads currently limit its applicability to narrow use cases. F1 tackles this challenge, accelerating full FHE computations by 3 to 4 orders of magnitude. This enables new use cases for FHE, like secure real-time deep learning inference. In short, our key contribution is to show that for FHE, we can achieve ASIC-level performance without sacrificing programmability. Thank you for your attention, and we look forward to answering your questions.